Okay, so today we shall discuss about few topics. Yet we are not uh, going into deeper into the top subject, deeper into the module, which is about non-deterministic algorithms. Okay, so before going into the deep side of non-deterministic algorithms, we have to understand a few terminologies and some basic concepts like decision problem. We want to start with the decision problem, and then we want to go for um, a very important concept of satisfiability. Okay, and then we will introduce several class of problems like NP class, P class, NP hard, NP complete. Hopefully from the next class onwards, we will start the main topic, which is
Assembly is recording the call. Yes.
okay. Let's start. Right. Just have a look what we did in the last class, so that uh, so in non-deterministic algorithm, normally we have three functions. One is choice, arbitrary selection element from a given set of data S, and failure is a function which represents an unsuccessful event. It may be a return statement, it may not be a return statement, it may be a break or continue statement. Okay, so then a success represents a successful event. After the success procedure, we can have an output of the algorithm, and we tried to demonstrate, we tried to illustrate the concept of non-determinism through an example of searching algorithm, where we are trying to find an element x in a given array capital A 1 is to n of n integers. So randomly we are picking up a position, and that in that position we just want to check whether user given value x is present at that position or not. So it's a one shot checking. So if the value x is present over there, it's a success, otherwise it's a failure. Okay, and in that because in one it's like equivalent to a random experiment. So if I conduct several times the experiment, then I may achieve a success. So it may take very less time compared to a large data set, compared to traditional linear searching algorithm, which are applicable on an unsorted array. So if you consider an array which is of very big size, and there if you conduct fewer experiments, random experiments, picking up randomly, a position index, thereby checking whether x is present at that location or not. So within few iterations, within few experiments, randomly, you can achieve a success, and thereby it can reduce the computational time with respect to as compared to linear searching algorithm. So traditional bubble selection or insertion sorting algorithm follows order of n square, okay, or maybe log n base 2 based sorting like not sort n log n, okay. So then what we have compared to those order of n square or order of n log n based sorting algorithms, if we apply I mean some kind of non-determinism like this, okay, suppose we have an array capital A which is storing some integers, and let's say we are creating another array of same size as that of A. The new array is capital B. Okay, and there I just want to randomly select a position index, and there I just want to check whether that position is already occupied or not. If it is not occupied, I will copy a value of A into that position. Otherwise, I will stop there. Okay, so in this way we can achieve a sorting in one shot. Maybe the B array may not be sorted, but if you conduct fewer experiments, within few experiments the array B may get sorted, and which will be uh, I mean, in which case computational time will be very less as compared to traditional sorting algorithms based on order of n square or order of n log n base 2 or order of log n base 2. Okay, so today we shall come to one specific types of problems which are decision problems. So what do you mean by a decision problem? Let us try to understand. Problem decision problem if its is either one okay, uh, algorithms which solve problems are called. And for your information, just I want to make a note of an optimization algorithm. Okay, so somehow it is different from an optimization problem. A problem uh, requires finding of an optimal solution subject to given cost function. Okay, it's called an optimization problem. Algorithms for solving problems algorithms. And time complexity okay. Let me give you some examples. Okay, like say in the graph G, we want to find there is any uh, Hamiltonian cycle. We'll talk about this later. What is a Hamiltonian cycle? Uh, Next, of detection of um, matching in a given also talk about bipartite graph and perfect matching. Number is a composite number. Okay. So we can take this. Okay, right. Another very important example in a graph. So of maximum click of G. So all these are decision problems examples. Okay. So to start with, let's start with this example. Okay, perfect matching in bipartite. So let's take an example. Let's take an example. Okay, so consider this bipartite graph. So it's a bipartite graph, and let me give some name to it. Let's say G1, G2, of which X is set of vertices, just like you know G I, okay, I is equal to 1, 2, 3, 4, and Y is the other set of vertices. Okay, such that such that Gi, comma Bj into G into I. Okay, already it is given here. Okay, this is the definition of a bipartite graph. Okay, so this is the definition of a bipartite graph. So we will not have any edge between the vertices which belong to the set X, and we will not have any edge between any two vertices which belong to the other set capital Y. But we may have an edge, uh, edge G I comma Bj. Sorry, so this is such that Gi Bj belongs to capital E. Okay, but I mean Gi comma Gj, Gi comma Gk is not possible. Similarly, Bj comma Bl is not possible. Only Gi comma Bj belongs to H set. So this is a definition of bipartite graph. This is how it looks like. Okay, and next we want to define what is a matching in bipartite graph. Bipartite graph equal to X union Y. Okay, so X union Y has a matching that saturates X if and only if S. Okay, so is equal to or less than or equals to for all S subset of X. So this is the definition of a matching. Okay. Next, what do we mean by a perfect matching? Okay, so if this condition is not violated, then we will not get any matching. Then, so for this example, let's try to understand the meaning of this matching. Okay, so let me see again. Changing the graph little bit. Right. So consider this example, ignore the earlier one. Okay, we have the ready-made answer for this. Uh, so consider this example. We want to find, let's say has 1, comma 3, comma 4. Just as we so it's a kind of a decision problem, you know. So we want to just check, find if this bipartite graph is even having a matching or not. So it's a decision problem. Okay. So we have let's consider a set of vertices A is equal to 1, 3, 4. Okay. Uh, then we will have n of S is equal to 1, 2, 3, 4 means let's say these are let's say this is G1, this is G3, and this is G4. Okay, and then NS will be NS will be equal to uh, you know 1 is connected to B2, 1 is connected to 4, so B2 and B4, 3 is connected to B2 and B4. Okay, right, and 4 is connected to B3 and B3 and B4. Okay, B3 and B4, right. So if I consider that it is B2 and B4, okay, then we have that cardinality of S no greater than n of S. So here, I mean, see that. Okay, let me ink the uh, with color. So this is one color, G3. We have taken G3. So G3 Mizuno. Okay. Then okay. So this is the situation. B2, B3, B4 are selected. Uh, if I mean B3, B2, B3, B4 we have right B3, B4, right. Okay. So if I select G1, now if I select, let's say pink color. So let's say we are selecting G1, B2, okay, and we have selected G3. So G3, B4, G3, B4, okay, and we have taken G4. Okay, so I'm sorry. Fine, fine. It's a good thing. Okay, so I make a wrong connection here. That's why it's not coming. Fine. So this okay. So it becomes a very good example where both thing we can demonstrate whether the bipartite graph is having a matching or not. So in this case, so I hope you can figure out the colors. So the red colors which are showing the possible edges to find a match for G1. Okay, means let me tell you like this, like this. So let's say this G1, G2, G3, G4 are nothing but they are four girls, and we have five boys: B1, B2, B3, B4, and B5. So we want to establish, boyfriend girlfriend relationship given four girls and five boys. So can I find a matching such that every such that matching means what? Matching means if I select, let's say, girl G1, girl G3, and girl G4. If I select girl G1, G3, and G4, so can I find a possible matching for these girls G1, G3, G4? And matching means, you know, one girl cannot afford two boys. Okay, so in that way, can I find a matching? So girl 1 is having two options: boy B2 and B4. Similarly, girl 3 is having two options: boy B2 and boy B4, which are shown as green edges. Similarly, G4 is having two boys, okay, option B3 and in this case B4, which are shown as blue edges. So now if I try to find a match, okay, so let's use a pink color. So this is not pink, I think purple, whatever. Okay, So this is the line. So G1 B2. So let me write the matching which we are trying to find out. Okay. Uh, Here. So one I have find, that is G1 comma B2. One match. So another is G2 and 4. This is another possibility, G2 comma B4, and we have G3 G3 3. Okay. So if I select this, then I can find the matching, and this is the meaning of this line. Okay. So SAS has a matching which saturates capital X. Okay. So capital X saturates means, this is the meaning saturates. I mean, no one girl is having two boyfriends. Okay, so that is the meaning of saturation. Okay, so G1 B2 G2 B4 G3 B3. It's a possible matching. So it's a possible matching on bipartite graph G. Okay, so I hope Rahul understand this. Are you okay with this? Fine. Okay, matching. We have found the matching. Fine. Next. So next what? But let's assume that this age was not available. This is there. Okay, that means girl 4 is having option B2 and B4. Okay, so girl G1 is having option B2 B4, G3 B2 B4, and G4 B2 B2 B4. So all of them are having options B2 and B4. That means two boys are available, B2 and B4, to be matched with any two girls among three girls. So naturally, what we will find that in that case, so, and what do you mean by S? S is the set of these girls, G1, G2, G3. And NS is the corresponding set of boys which are being which are tried to be matched with the girls available in the set capital S. So we are trying to find a match for G1, for G3 and G4. But the set NS is B2 and B4, because G1 is connected to B2 and B4. So B2 B4, G3 is connected to B2 B4, and G4 is also connected to B2 B4. That's why NS is B2 B4. Okay, so here we can find that the cardinality is S, which is greater than, the cardinality of NS, which violates this condition. To have a matching, this should be satisfied. The number of girls must be less than the number of available boys. Okay, then only we can find a matching. And matching, we are trying to matching from this side to this side. So it's a direction dependent, which is not which is assumed here, which is not considered here. So it's a direction dependent. Okay, let me come to this point later. Okay, so this condition is violated. This condition is violated. So hope you understand. So in that case, we can't find a matching. So can't find a matching on G. Okay. Okay, fine. Now coming to perfect matching. So a matching matching on G, perfect matching the matching saturates X for is equal to. Okay, so we have to find a match for all the girls belong to the set capital X. Then I can find, then that matching I will call as a perfect matching. Okay, so the question is the bipartite graph containing any perfect matching? So this is a decision problem. Okay, so let us try to find a perfect matching here. So can you find the perfect matching here? So G1, B2 and B4. So let's assume G1 and B2 are matched. Then G2 and B1, it's an obvious because B1 is connected with only one girl, G2. Then G3, B2 and B4. So option is G3, B4. And G4 is either B2 or B4. So it's not possible. So let's disconnect this. Let's assume B2 and B4. No, it's not possible. So B3, B5. So B5 and B1, they can take a single girl, G2, right? So that's fine. B2, B3, B4. G1, G3, G4. B2 is connected to G1, G3, G4, and B4 is connected to G1, G3, G4. So no, we will not have any perfect matching because G1, if I remove this, okay, then what is the picture looking like? See, right. So this is the scenario: G1, G3, G4, but B2, B4. This is also absent. Okay, so two boys, at this moment, if I find a matching for G2 and remove that portion from the bipartite graph, we come to this scenario. The cardinality of S is not less than or equal to the cardinality of NS. So for this sub graph of the bipartite graph is not having any perfect matching, and according to dynamic programming, we come to the conclusion that the overall bipartite graph cannot have a perfect matching. So I hope you understand this. So in our example, containing perfect matching. Okay, so this is the explanation, uh, and it's a decision problem. Okay, I hope you understand. Next, coming to next problem. Uh, so this is done. Explanation of perfect matching in a bipartite graph. So Hamiltonian I will talk about later. Okay. So now coming to satisfiability. Okay. Acha, let me talk about another problem. It is related to graph. Another non-graph problem we have. Check if a number is composite number or not. So let me tackle that problem. It's example 1, example 2. Okay. Example 2 on composite number. Okay. And what is a composite number? Let's try to understand. Okay. A composite number. So a composite number is a number which is divisible by which has at least one factor other than a composite number. N is a number a num which has at least one factor other than, you know, 1 and n, or not. It's not a prime number. The opposite of prime, is a composite number. Okay. And very easy to understand. So now a non-deterministic algorithm to check for whether a number is a composite number or not. Okay. Say input an n, then um, call a function choice. Okay. From, a set of all the natural numbers. W. Okay, choice W. So here W is a set of all natural numbers. Okay. So, and here choice W only selects the number that is a factor. So it's a factor I am trying to randomly select. Okay, so choice W. So let assign to a variable f. So next, what I want, if uh, if perfectly, say that integer divides. If integer divides n, then it's fine. Immediately I can display that n is a composite number. and it's a success. And uh, if it is not true, then it will come to at this line and will execute uh, failure. Okay. So if I, and this is a non-deterministic algorithm, and if I want to compare this with and a deterministic algorithm, my algorithm would be like this. Algorithm, and that is like input in, okay, and then for I equal to 2 to n minus 1, it's a greedy approach. So for I equal to 1 to n minus 1, we just want to check if I, so let this be f divides you know say n is composite number, and if f is equal to n, then you can say that display n is not composite. Okay. So here, the time complexity for this time complexity here, Tn is in the order of n, and here Tn order of 1. Okay, so this is the advantage of using uh, mm, uh, using a non-deterministic approach. Okay, if you have any question, you can ask me, because I will go to the next topic. Okay, which is now it's a satisfier. Okay, so what it's I mean, the motivation is concept is widely popular. Artificial intelligence, and it it mathematics. Okay, so let Boolean variables are denoted as you know x1 dot xn. Okay, takes a value 0 or 1. 0 means it is signifying false, or okay. Literal is denoted literal. Okay, it has suffix ij, which may be equal to xi, or
আট এগুলো তো মনে থাকে না, এগুলো তো ভুলে যাস কি করে বলিস? আমার বেলায় মনে থাকে, যখন ফাটাবো বলেছিলাম তখন যাওনি কেন? যখন পাঠাবো তখন তো পড়ছি লিখেছি একটা কি পড়ান না।
okay, so a literal is denoted as lig, which will assume a value xi. Okay, Boolean variables, they may be thought of as random Boolean variables. Okay, so Lij, which may be equal to xi or not of xi. So this symbol, is known as not operation. Okay, not operation, not, Boolean not get. So next, what we have, propositional formula. Okay, is normally denoted as phi. Okay, so these are the things. So these are some Boolean variables. These are called literals, and these are phi, propositional formula. Okay. Now what we want here, we want to create a decision problem where we have to check in that decision problem, okay, whether a given assignment is satisfying the given formula or not. So what is an assignment? I forgot to tell you about assignment. So assignment is denoted as x, 1 comma let's say 2 comma let's say then x3. These are actually prerequisite. I mean, whenever actually someone is teaching you this topic, so he has to assume that you know this. Okay, but still, I will try to cover as much as possible. Okay, so this is an example of an assignment. Okay, x1, this is AND operation, the of this one, and this is OR operation. Okay, so a decision, a satisfiability problem is a decision problem where which requires check a given assignment, such an assignment satisfies the given propositional formula. Fine. Okay, propositional formula. So this is a satisfiability problem, and it's a decision problem. Its answer will be either yes or no. The assignment is satisfying yes or no. Okay, fine. Okay, now we have two very popular form of propositional formula in the context of satisfiability problem. We have to know this. So one is, you know, conjunctive conjunctive normal form. So it is represented as everything you are understanding, so no need to explain that much. So I am showing you only the mathematical model of these topics. So it is represented as okay. Ci, small ci, this is ci, and you know this will have so this is I is equal to 1.
Sir,
Okay. Yes.
একটুখানি স্যার একটু জুম করা যাবে?
ঠিক আছে দেখছি।
ওকে স্যার।
Okay. So this is represented as, you know, the AND form of all Ci where I is equal to 1 to k. Below it, okay. So where Ci equal to literally j equal to 1 to k, for example. Okay. Okay. And where Lij xi or not xi. So this is the model, conjunctive normal form. Just for your convenience, I will try to expand it so that I can visualize the model. So this thing, okay, CNF, you know, now you are getting what is the meaning. So here we have okay, and here sorry, this is similarly here we may have L. I hope now it's so here is one. Uh, so on. So this is the form which is known as conjunctive form normal form, and we want to find whether a given assignment is satisfying this given conjunctive normal propositional formula. Okay, that's why this is a very popular problem, conjunctive normal form. Okay, satisfiability, conjunctive normal form, satisfiability. So next coming to its counterpart, which is conjunctive normal form, DNF. Okay, I'm about to close within 5. It is represented as its exactly counterpart. Here OR operation, here AND operation will be there, and the alternate. So just writing the formula. That's all. Okay. Okay, so DNF, let's say DNF satisfiability. So, ability problem, which is a decision problem. These problems are very difficult to solve. Whether we can have a proposition or formula which can satisfy this DNF. Okay, so decision problem where find uh, find an assignment that can satisfy the DNF. Okay, so it's a decision problem, and that's not a problem. That okay. So and this an algorithm can compute can solve decision problem in real time complexity. That is, it is likely to be equivalent deterministic time complexity means f of order of some pn. Okay, it is likely to be equal to a deterministic algorithm. Okay, so that's fine, but if we want to find the number of assignments can satisfy the DNA, then the problem becomes uh, counting problem. More specifically, is called in the data. It's called approximation counting problem. Okay. So if it is equivalent to a deterministic algorithm, then this algorithm is can be called as uh, simply P problem. Okay, so this is the first time we are introducing a P class problem. Okay, so by doing this, we randomly select through the choice function an assignment and just check whether that assignment is satisfying the DNF or not. If that's so, success, otherwise failure. And if that is failure, so always we will try to conduct a number of experiments, random experiments. So that's like trial. Okay, that's equivalent to tossing a coin. So we are tossing a coin 5 times, and that is 5 trials we are conducting. And out of 5 trials, we may have 3 times head and 2 times tail. Now the question is, if I want the head, so 3 out of 5 trials giving me success result, whereas 2 trial out of 5 trials are giving me failure. So there comes the probability. So probability of getting success is 0.60%. Okay. So if I model a decision problem that say uh, toss a coin and tell me whether it is coming head or not. Okay. So that means I have to conduct several trials. Then I can say yes. If I conduct, you know, if I conduct large number of experiments tossing a coin, I may get an answer that I will have answer equal to head with the probability, let's say 75%. So this is an answer. Okay, the non-deterministic answer. So I am getting an answer head, but with some probability. Similarly, we are trying to check whether an assignment is satisfying a DNF or not. So we will conduct several experiments. Every time I will check whether that assignment is satisfying the DNF or not. Okay, so the number of successes, the number of trials in which we are getting success divided by the total number of trials will give us the probability. Okay, that a given assignment will satisfy the DNF problem. Okay, so so this is and that algorithm, always it's solvable within polynomial time complexity, order of n square, order of n cube, whatever. So it's a P class problem. That's why polynomial class problem. P for polynomial time complexity. Okay, and those algorithms which are not solvable within polynomial time complexity, order of Pn, those are not called P class problem. Those are called NP problem. Okay, so the algorithms which are not solvable within polynomial time are classified as NP class problems. Classified. If, so this is NP and NP class problem. Okay, but if I model a problem, it's a counting problem. Okay, so I just want to know how many assignments are there which are satisfying the DNF proposition formula. Then what can I say about that? The answer, how many number of assignments? So let's take an example. Then you can understand why we are talking so much and why these problems are becoming so difficult. So that's why in terms of in terms of compatibility, okay. So what we are interested in our literature, that we are actually interested on computability. Fine. So example, let's say let we have a formula. Okay, a formula phi is is a function of, you know, x1, x2, comma x3, the three variables. Okay. Then we may have an assignment. We have an assignment as, you know, some sort of okay, one, let's say, and two. So this is my assignment x1 and not of x2. And it denotes, you know, it denotes x1 equal to 1 and x2 is equal to 0, x2 equal to 0 because of the NOT operation, as it is AND, so it will be 1 if x1 equal to 1, x2 equal to 0, and x3 is assumed to be, let's say, 0. So this is a possible assignment 1 0 0. My question is whether 1 0 0 is satisfying a DNF based on only 3 Boolean variables x1, x2, x3. So in that case, how can we answer? Okay. So total number of possible assignments is equal to, you know, 2 to the power of 3 is equal to, okay. So we can check for all the 8 assignments whether they are satisfying the given proposition formula phi or not. So number of assignments out of 8 which are satisfying them is the number of assignments which are satisfying the DNF, for example. That is the counting. Okay, total number of possible. So in this case, in worst case scenario, the number of assignments satisfying the DNF variables, okay, is what we call as DNF counting. We call it as a DNF counting. It's 8. 2 to the power of 3. Now, if DNF formula is based on, you know, n variables, naturally DNF counting becomes equal to how much? 2 to the power n? Right, so 2 to the power n it becomes. So what is the point of discussion finally we have? That is, any deterministic algorithm, let's say using greedy method, can be, will be an exponential time algorithm. So surely this is not a good algorithm, right? So 2 to the power n, it is in the order of 2 to the power n. So with the time complexity here, we have t is equal to order of uh, of n. So I hope you can understand why we are trying to come to the picture. We have definitely a deterministic algorithm, but it is taking an exponential time to the power n. Even only solving this kind of a very basic problem. Okay, DNF counting. So I will stop here. Next day we will switch on to uh, NP class problem in more detail, and we will discuss about Cook's theorem, satisfiability theorem, and Cook's theorem in general. If you have any question, you may ask. So I hope no question. So stopping the recording.